So everyone is able to hear me, right?
Yes.
Okay, so today we are going to hold on a second. I'll just quickly update it. So today we're going to discuss the Google search typehead suggestion. I'm sure you guys know about what exactly this is, but let me explain in summary what we mean when I say Google search typeahead. You guys might have observed that whenever you start typing a search query on a uh, Google Google text box, the Google starts suggesting you some of those things just below your query that you might want to be interested in, right? That's what is called type ahead. And in designing type ahead can be a tricky thing, uh, especially because there's a lot of data which is constantly being pulled from the server, and if you pull that kind of data, that amount of data at such a speed directly from a database, then it's much more likely that it will crash pretty soon, even for a small scale. Forget about going at a scale which is of a Google scale. Even a small number of people can crash your server if you are directly fetching it from the database. So that's what makes it difficult, um, primarily because of two reasons: that you need speed as well as there is loads of data. So, and both of these things doing at the same time make it more complex. And we will discuss the techniques to deal with such problems, and we will see how we are going to tackle the client side things, the server side things, and how we can accomplish everything. And as usual, I will be following my template, which is: first I go through the requirements, and then I go to the capacity estimation, and then I suggest some APIs, and then probably a design, and then advanced design. So in this case, there is no database design actually, which I need to change it. Yeah, there is no slide. So I wanted to design the database for this first, but then I thought it will be pretty in vain to design such a database, because it is obviously clear that we definitely don't want to store it into some kind of relational database. So there's no point in designing like that. We'll go ahead and start designing the way which we are thinking from the start, early point. And then we will see what we missed and what we could have done better in the last. So let's start with the functional requirements and non-functional requirements. The requirements are pretty simple. Requirements is whenever you start typing your search query, your service should suggest 5 search terms based on whatever you have already written. And then non-functional requirement is obviously it should be fast, means highly available. Your query response time shouldn't be greater than 200 milliseconds. And but you can compromise on some of the consistency of the information. For example, probably the latest suggestion is something, but you are showing the suggestion of 2 hours back, the data from 2 hours back. That should be totally fine. You don't need almost all up to date data all the time. You can have compromises over there. Have I explained clearly what do I mean by the second point in non-functional requirement?
Yes.
Okay. So then comes the capacity estimation. Again, don't spend so much time on it. You're trying to gauge how much speed you are looking and how much capacity, how much storage capacity you need to have. And I think I missed here the network capacity. I will leave up to you guys to calculate it based on all these assumptions, and tell me in the comments later on what you guys think will be the network capacity of the system. So roughly imagining that, let's say you have 500 billion daily searches, which will turn out to be 60,000 per second. 60,000 per second queries in your system service. And then you can say that, let's say 20% queries will be duplicate. For example, in the current scenario, the duplicate queries will be somewhat related to, let's say, coronavirus, unemployment rate, or whatever is hot in the current market today. So those kind of queries will be queried by multiple people at the same time, and you can consider them as duplicate, and you don't have to recalibrate for each user. You more or less already might have calculated. You have to just redirect and fine tune based on the person who is querying it, right? And then these queries are consist of words, which is a dictionary plus different types of nouns or other phrases which are probably not even there in the dictionary. And at some point you want to combine some terms and treat them as a single keyword in your database. So these can be considered around 100 million. That's the assumption. And then the capacity estimation, as usual, we do. We just assume outrightly some of the baseline things. Like we will assume that each word has an on average 5 characters in it. Every query has two words. I should have written three actually. Every average query has 3 words, which means 5 words into three means 15 characters. And how many 15 characters per query are there? Then we have 100 million unique terms. Then we calculated it will turn out to be 3 GB of data storage space just to save all these unique terms on your storage somewhere. And then if you calculate 1 year storage, and these unique terms will keep on growing every now and then, because every day there is something new happening, and for that people will start querying, and for that you have to uh, proactively create such terms which get added to your database. And I'm expecting 700% growth, which is around 21 GB. So that's the amount of storage you will need for storing all the terms which you want to uh, provide in your search suggestions. So as you can see that storage is not much of a problem. 3 GB, 20 GB, it's a small issue that shouldn't be your concern, but speed should be, because you are getting a query of around 60,000 requests per second. So that should be your main concern. Let's move to APIs part. So I looked around. Google does provide some APIs. I don't think they have API for your normal search, which you do on your Chrome browser or Google search box. They provide API for custom search. You might be seeing that on some websites, you have one search bar called Google custom search bar. These APIs from those, and I'm sure the real Google APIs will look something similar. The get UI will get API, which will get you the list of all the result, will look something like this, and response will be something like this. So it is complete copy paste. I didn't think much, and I'm sure the format will look something like that. So let's move ahead. Before we move on to try, actually, I want to know you guys' opinion that have you ever heard about the term try? It's a kind of data structure, and I'm sure you guys are practicing coding interviews in parallel. You must be doing problems based on try, string manipulation problems. I want any one of you to give a try and try to explain me what try is, then I can go ahead and build upon that. Kesha?
Yes. So, as far as I know, like try data structure, we can make a tree sort of structure in which there will be every class will be having array, like
Mhm.
an array of all the characters one by one, and it will be having is and like we can modify the class structure according to our needs. But I have done 2 3 problems in which I had used is and is equal to true or false, that it will say that this word is like this last index, is it the end of the word or not. And in some of the cases I have taken like a string word in a class, it in which you like it will store the whole word of the like of the whole word as well. So
Right. Yep, you're right. So try is used in those scenarios when you have to search from a big text, and you want to somewhat store that text in a format which is very much suitable for search. And this try structure is exactly used for that. Search in a big text kind of file, and you don't know the complete query at once, and you are building character by character your query, and based on that it will keep traversing the tree, and at the end you will reach a node when you end a query, and you will have some information at that point. So Kesha, you did explain it properly. And if there is anyone's mind doubt that what exactly try is and which is not clear, please ask. I might build some more introduction around it. So anyway, I wanted to explain what I guess what was the historical region. So generally, I think the dictionaries were first you were using this kind of data structure, online dictionaries. The problem, like suppose someone asked you to put a dictionary online somewhere, and how do you port your offline dictionary to online? What kind of data structure you are going to use? So that's when I think it was decided that they are going to use try, and each node will consist of 26 array, 26 length array, and each index of array will represent one character, A to Z. And as uh, the first layer will have 26 character, one node, and then each cell of that 26 array will point to a next node, which in turn itself will have 26 rows. So imagine 26, and then at next level there are 26 into 26 arrays, right? So each node itself is a 26 array, and you keep on building that. So that turned out pretty efficient, and then they started optimizing it, that probably at each level you don't want all 26 length of array, because that will be waste of space. um, so they started optimizing it, condensing it in some form, and then that's how I think this try structure was born. The image in front of you is more like the optimized version of the try structure, where we are clubbing multiple characters together because they are coming pretty frequently. That's how we clubbed in together. And the number which you see is just beside you, any one of the character here, this as of now you can think of represents the count, how many times that query has been searched. For example, if someone wants to search TED, then your search will start from here. It will go to T, then it will go to TE, then TED, and it once it reach TED, which means we have searched it once, and this 4 will be incremented once more. So this TED has been now searched 5 times. Same thing happening with all other counts. So as of now, imagine this as a count of search. We will see what we can build upon this count thing, and how much enhancement we can do on this thing. But for the sake of understanding, just imagine this picture of a try, and this number written just beside the node as the count of times that query has been searched. All right, keep this thing in mind, and I will build it upon build this everything on top of this one. um, So there are a few things which I want to discuss basically before even going to this try data structure. Okay, let me discuss verbally. So what problems do you think your 60,000 search per second will have when you have this particular try in memory? Can you see any problems? Probably your data will become outdated pretty soon. You have to update this try structure every now and then. Or what if your word structure remains too vague that you are not able to store on a one single machine? Even if you are able to store, you are not able to serve all the traffic from that node. What do you want to do?
I think this try has scalable issues. Like if we even if we store the whole query in one tree, I think the moment we will try to search from this tree, it will be pretty slow.
Yes, so think about it. This one particular tree has been searched by 60,000 queries per second. Definitely, it won't be scalable. So, to solve that problem, what you are going to do, probably you will copy the same try in multiple nodes and distribute your 60,000 traffic in those multiple nodes. That should solve your problem temporarily, at least by replicating. But that also won't be enough at some point of time. So one try structure will become so huge that you have to break the try in itself into multiple parts. So that's kind of partitioning we are going to do. So the partitioning logic seems to be straightforward to me here. You want to partition based on the alphabet start. For example, you can bifurcate try in such a way that A to D is in one try structure, and then D to next four characters are next try structure, and so on. So now you see that you have bifurcated your query based on your alphabets. The root node based on the root node, right? Here the root node is A. No, the root node is this, but the starting point, if you see, right, T, A, I, these are the three starting points in the trie structure. Similarly, you can break it down further and partition it. But what happens if you partition it? Again, you have to copy into multiple nodes. Again, you have to do the same process. And then it will add some complexity. We will solve that problem. Another piece of complexity is how you are going to update this trie. As you have seen in your tree data structures, updating and even changing a few things can be pretty complicated and intensive, quite quick in the tree database. So you want a mechanism which can update this tree on the go. Imagine 60,000 queries are coming to this tree, but at the same time, you are trying to modify some of the cells. That will be very much catastrophic. So the solution to that will be probably just like any other solution in the world or any other solution till now which we have discussed. Whenever the computation process is extremely intensive, we try to put that computation process uh, as an offline solution. As an offline solution, meaning it is not in the way of your real-time flow. So we will have to figure out to compute this trie structure when it doesn't come in the way of search. And once you have already updated it, just to start redirecting your traffic, which was coming to this uh, old try to the new one, which is the updated one. So that kind of techniques which we follow in Twitter also, we saw that we pre-computed the home timeline for the users just because it was very compute intensive, right? Same technique is there, just a different structure approach. All right. And then there are multiple other issues, like in some region some type of query will be more highly likely to be searched. In US, there will be some US some celeb which is pretty well known in US. Probably, let's say, imagine some football celeb which is well known in US, but no one knows outside US. So that kind of search query will be relevant, localized to US, and you want to cache it in US itself. So you guys already know that what we do when we have geographically significant data, which is not applicable to all the geographies, but some particular geography it is significant. Where do we store such kind of data, especially when it is not changing pretty soon, regularly? The answer is CDN. So we will put those kind of data in the CDN, which is pretty geography intensive. And in general, we all use the cache, which is generic cache, which will come in front of database or wherever we are storing the try, just in front of that, so that we don't have to go to database again and again whenever we want to make a search. Instead of database, we will first search cache. If the data is available in the cache, we will fetch that data, and that's it. We don't even have to go to database. But in case if it is not there in the cache, then we will fall back on directly querying the data from the database, and then updating the cache also, and returning the result to the client at the same time. Right, so there's a couple of things which I discussed, which can be optimized in the basic solution, and then I can move ahead in the uh, more advanced solution. If you could gather, there are two major things in our design as of now. First major thing is serving the result to the client. There are 60,000 queries coming per second. You need to have a good thought process around how you are going to fetch the data, how you are going to serve it. That should be your first approach. And then second approach is that you are serving, let's say you are serving the data fine, but how you are constantly updating your tree trie structure which you have just created, so that it doesn't affect the first flow but still happens. So that's how we bifurcated our design into two parts, and we will discuss one part, one by one part, and we will see what each of these components mean and why we have put all these components. Any doubts till now? I'll assume no. So let's start from this client. As a client could be browser, mobile, or any other device wherever search is possible. You fired a query, it will go to the load balancer, obviously, because now you have multiple servers running, which will be serving your traffic, because 60,000 per second is definitely um, not good to be served with a single server. So there are multiple servers which will handle your request. And then load balancer is the one which is going to maintain, which is going to evenly distribute your traffic into multiple servers. And as we have already discussed, that load balancer can be of different types. How much configuration can you do based on in the load balancer itself, and whatnot. I'm not going to discuss the load balancer again, but I will encourage you to go back and see the load balancer discussion on my YouTube channel, which I have already uploaded. And once we come at the load balancer point, it will redirect to each of these servers. And one thing which I wanted to discuss for a while now, which I just mentioned here, but won't go into detail, there's something called consistent hashing. So why do we need consistent hashing? Is to have a flexibility around the number of servers, because sometimes you will increase your servers depending upon the peak traffic. Sometimes you are going to decrease your servers depending upon the traffic, or even sometimes some of your servers will keep crashing. What do you do in that case? How your load balancer is going to handle, how you will make sure that your application doesn't start malfunctioning in those scenarios. That's when we use consistent hashing. And consistent hashing enables you so that load balancer can properly direct all the requests irrespective of all these scenarios. We'll discuss consistent hashing at some other point. But as of now, imagine that load balancer is distributing your request among multiple servers. So what will happen? Your query came here to the load balancer. Load balancer redirect to, let's say, one of your compute servers. You want results now. First server will ask cache that, do you have such result of such and such query? Let's imagine in that case, yes. Then your request will return from here, and you will be able to serve the result here. go back to the client. That's it. You won't even have to do anything. But another scenario is, let's say your cache doesn't even have anything. What do you do in that case? Then you refer your zookeeper. Just like I told that you are doing partitioning based on alphabetical order, so zookeeper is the good candidate to have such kind of configurations. And zookeeper is generally used to store such configurations. And it's a Apache based software product which you can directly employ in your application. So let's say it consults zookeeper. It sees that which particular tree set is responsible for my query. That's where it should redirect. So let's say this tree set one is the one who has stored this query's result, and it will go to this trie set one, and it will fetch the data from it. As you can see, there are multiple tries here. Why? Because this trie set will have same data replicated multiple times. That's why it is called trie set. And each trie set will have same amount of data, same data replicated multiple times. And this trie set will have different data, but each trie in this set will have same data replicated among themselves. Understood? So we are distributing as well as replicating. Within any trie set, we are just duplicating the data, but among trie sets, we are distributing. These have different data. All right. So this is the flow, which is general search flow, which you probably would want to explain first. And this design is not much different from any other system design. Typical workflow is there. You are getting a request, you are utilizing load balancer to distribute the traffic, you have multiple servers, you have cache, and then you have some kind of storage. In other cases, we generally had data, some kind of relational database when I represented the previous search. And here we will use try. I have still not discussed how we are going to persistent try in our storage. I will come to that later, but just imagine there is something like some database which is going to store try and fetch our data from there. Correct?
Yeah.
Okay, so we are about to run out of time. We have 8 minutes. So I'll quickly go to the another one. How you are going to update it. So imagine you had, you remember you have fired a query, right? This went to this request flow. But what else happens in that case? Your query was logged in some temporary storage, some kind of file system. Let's say HDFS. Your query will be logged in this log storage, and then after, let's say, 1 hour or 2 hour or 3 hour, whichever time period you assign, all the queries within that time period will be collected by your MapReduce cluster. So MapReduce cluster's job is to collect all these queries, process all these queries, and put it into the database which contains trie, and then put it into this database, and then some server will basically update the trie dataset, which are in memory. So till now we saw the client, we logged our queries. We have we have one MapReduce cluster, MapReduce job, which pulls in query from your query log and then consults query weight generation. So let me explain what query weight generation is. In the first image, I told you guys to imagine 15, 11, 5 as count, simple count, number of times that such query has happened till now. This is very simplistic measure. Google or any service at that scale doesn't like consider count. It has thousands of things which it needs to take into consider before ranking the search terms, right? For example, Google might be looking at your own Google search history, or how many people are querying this query at the same time, which particular regions are contributing, or probably they are also employing some machine learning model with thousands of input variables they will employ, and ultimate output of that process will be, it will give you a numeric or decimal number as a weight for that particular query. So this MapReduce cluster will take query from here, take weight from here. Now we have a pair that we know the query and we also know the weight, correct? And this query will be combined by MapReduce cluster. This pair will be generated by this MapReduce cluster, and that will be stored in DB. In this case, we will use Cassandra White DB. Till now, it is clear na, why are we storing query as well as weight? Because these
Yes.
both the things, yeah, because this.
Anish,
Mhm.
like, is there any specific reason to store this this key value pairs in Cassandra? Like we have like lots of key value pair data structure, right? So is there
Yeah.
any specific reason?
Well, specific reason is it's a wide column storage. As you can see that you can in the next slide I wanted to show you. This is how it looks like. It's not farce, it's phrase. It's a phrase. So phrase one, phrase two, and you have one column called time, you have called weight. You might have multiple columns based on different weights. That these columns, for each column, each phrase might not even have value. Basically, I'm trying to say that will be sparsely populated table if you would do in relational database.
Okay, okay,
So
got it.
that is one case. And then the kind of operations which we are doing here, right? We want to read pretty heavy at the same point. And generally in such scenarios, relational database is not very good candidate. I want you guys to think relational database only in case you have extremely huge scale, but your consistency is not important. Your consistency is also important. These days relational databases can handle traffic. I'm not saying they are not scalable, but they are scalable, but after a point that doesn't make sense for search terminology or even um, I think around 10 million or so rows they should be good enough for a relational database, but beyond that I think it will become very difficult to query and write at the same time. In that case, you want to have some combination of relational as well as NoSQL database so that you can handle the traffic. NoSQL databases are very good at persisting and fetching the information because they don't do so much of a join and merge operation in the database itself. It more or less it's a flat, uh, flat schema. You don't have to go to multiple levels just like you would do in relational database. That's why we picked Cassandra white column database. It will be useful to in writing heavy and reading heavy.
Okay, got it. Thank you.
Got it? So let's continue in the other call. I think this is going to end soon. Yeah. Yeah, so we are using MapReduce because imagine there will be so many queries within 1 hour, right? And there will be so many people querying with many duplicate queries and with so many other parameters also along with query won't be just it. There will be so much data related to that query. On the go, you have to figure out which queries were duplicate, and within the frame of that time range, you want to know that how many queries, such and such queries were there. You want to count it, what were the different sources, all those processing which you have to do. And if you observe that this processing can be distributed, for example, one query term or let's say similar query terms can be combined into one set and some operation can be run on them together. And similarly, you can bifurcate data into multiple runs and then count together. Typical MapReduce cluster. You have 10 queries, you have you want to know that how many times these queries came from different sources, then you assigned one node for each query. And no, first map will basically take all these queries and it will count into separate buckets. And then reduce job will pick up these buckets, search, filter out all these similar queries and count them and then produce the result. So at the end of the map and reduce job, you will have the pair of query and the count. I took count just to explain it, but it could be anything. I encourage you guys to read more about MapReduce cluster and in which scenarios they are useful. But in general, that's what I'm suggesting, that once you have a huge set of tasks to do, some processing to do, and visibly you can see that that task can be broken down into multiple chunks, and individually some logic can be applied on the multiple chunks. And once your outcome is already there in the multiple chunks, then you want to combine the result together and produce an ultimate result. The first process is called map, which where we applied some logic on multiple chunks. Second logic, where we combined all the result, is called reduce, and that produces the ultimate outcome. And you can put your processing logic and reduce logic in your MapReduce cluster. So that's what we are doing here. So we are picking up query log, we are doing some processing, and then we are getting weight from the query generation, weight generation service, which I have not discussed at all in detail because that can be different, totally different topic altogether. And that's a pretty wide field, that how you assign weight to a subquery or a query. Someone is messaging me. That's fine. Let's go ahead. So we got the pair output, query, related weight, and all other data. We have put it into the database. Now this server will run every 1 hour, let's say, and it will update the trie sets, which we have seen in this one. It will update these trie sets, but it will not update exactly these ones which were used in the production. It will have a copy of them. It will update those offline, and once this update is complete, then all the flow traffic, which is search traffic, will get redirected from these to these. That swap will happen on the go whenever there is a update completion. So that is one method, that you copy all the current one, store it into the separate storage, and update that, and then swap it. Keep doing that. One official term can be that master slave. Imagine this this set of trie sets can be a master, which is basically responsible for searching. This can be slave. All the data in this one is already copied in this one, and then it is being updated. Once it gets generated, then the role swaps. This becomes master, another one becomes slave. Okay. Well, someone is saying something I'm not able to hear. Can you send me into the chat instead? Your voice is breaking too much. I can't hear anything. Okay, I will go ahead. Please personally message me. I couldn't hear you at all, whatever you have asked. Um, Message me separately. I will answer it. Till now, I think everyone else, are you guys good? Satbir, Saloni, Devashri.
Yeah, because
Okay, so let's go ahead and see what else we have got. And these are the some pointers which I thought about that we should be discussing, but I think most of these things I have already discussed, but still let's go through. The weight of search at the ending node, which you have already seen in this table. So whenever you search it, you update the weight on the go. In our very simple design, we did that. But in our advanced design, we were employing a service which was dedicated to calculate the weight, which was providing this weight on the real time. and we were updating try based on that. And what else? Yeah, there's so one actually critical thing which I missed out here. If you see this try data, whenever search query comes, every time you have to traverse the tree to actually reach that particular node. That might not be pretty scalable for you, because if you think that 60,000 query came per second and out of that 20,000 query came for just this 10, every time you have to pass this tree and reach at this node. So to handle those kind of things, what happens, the starting node, which is T, itself stores so many words which are frequently starting from T and are hot right now. So let's say in front of T, you will immediately store T TED 10. So whenever user types T, instead of scrolling down and searching through this thing, they will just immediately pick up these words and return it. So that will, again, that is a pre-processing step. As I already told, whenever there is so much compute logic, we try to pre-process it, right? So that's kind of pre-processing which we want to do and put it all the search terms here. And also that is going to filter out the number of search terms based on probably the weight. The top 5 elements under this tree whose weight is highest will be picked and put in front of this. Not just the list, but it will filter out which elements to put. Correct? So that was one important part. But as you can imagine, there is a problem in this particular step. Problem is each node will have at least 5 search terms stored alongside it. And if you have 100 million nodes, imagine 100 million into 5, that became 5 million. So when we might run into in-memory storage, and it will create problems. So what we do, instead of storing, let's say, full word, we store the end node's link pointer. This T will have a pointer stored for T TED 10. And whenever someone searches T, we will immediately go to those pointer and we will fetch that node. Is that clear now?
Yes.
Okay, so what else we missed? Update the try periodically offline every hour and move the traffic to new try. We have already discussed this. And what else? We can optimize the frequency with as simple as counting strategy or combine it with how old the search was. Yeah, so one of the parameter which is probably super important in search, Google like search, is how old that search was. If something was searched like 1 year back, then probably it doesn't make sense to put it into the cache now, right? You want to have a mechanism to have the relevancy of those searches uh, already up to date based on the current scenario. So one technique which can be used here is called exponential moving average. So in simple terms, exponential moving average basically gives more importance to the recent data than the old data. As the data keeps getting older, less importance it gives. And this exponential moving average has a simple formula. Exponential because as data gets older and older, its importance gets reduced in exponential manner. The immediate data is super important. Let's assign it value 100, and the old data might not even have value of 1, right? If you go see the graph of exponential growth, you will see that what I mean. Right, so they can employ such techniques, but again, as I told that we are not going so much deep into how we are going to calculate the weight. And then you can apply policies. Let's say some of the results in some countries are not to be shown based on that country's policy. And what you can do, we can put a separate filter server just before you serve to your client and filter out based on the policies which are relevant for that particular situation. right? And this policy set of policies will be different for different country, different levels, and you will create your logic in such a way that on the go at that time it will fetch the relevant policies, it will sort all search, and it will remove all those filters which you do not want to show. Whereas when you go to the other region, it will fetch different set of policies, and probably the element which you have removed from the previous instance will be shown now, because now the policies are different. And then there will be that it makes us thinking there will be some kind of policy engine where you can provide some parameters. Okay, I am querying from this country with so detail, give me all the set of policies which are applicable in current scenario. That policy uh, engine's job will be to collect all those policies and give it to you. All right, so I think this is all I wanted to discuss. I could think of. Is there anything else which you guys want to ask before I move further?
Avnish, I have one question. Do you think it would be a good idea if we create a separate try set um, for hot topics like for example we are having this COVID-19 situation. Do you think it would be a good idea if we create a separate try set for all the information which are for COVID-19?
It will be a good idea. However, what I wanted to put that hot topic in the cache itself. You don't even have to traverse the tree in case the
Okay,
topic is hot.
yeah, that makes
Your
sense.
query will be ready-made kept in cache
Correct.
in something like key value pair.
Hmm. Yeah.
But if cache is not enough, generally caches are costly, but you have huge set of hot topics which you want to save, then in that case, definitely it makes sense. Okay, so this one I have already described that this is what schema will look like in your Cassandra type of database, column wide. You can keep adding new columns for each row, and it won't affect the whole all other rows. And what else we missed from this one? We missed actually almost everything. We we designed simple search, but we missed most of the good features which Google already has, and which would have made our design extremely complex. But think through and research all these topics, how Google has done it. There are so many blogs and videos all there. You can search on each of these topics and you will know. For example, spell check. Whenever you query, you see, right? Google still searches with the wrong word and suggests you probably you wanted to search for this. How does it do that? So I imagine that will come somewhere here in this flow. Whenever you searched it, there will be a service in between this before even going to our main servers. There will be a service which will already have a ready-made mapping of commonly wrong words with the right words. That is simple strategy. Next level, if you want to improve the system, then we have algorithms for fuzzy matching. There's a set of algorithms called fuzzy matching algorithms. So the job of those fuzzy matching algorithms is they correlate to different set of information. So in your case, you will have two queries. One is right query, one is wrong query. And based on that algorithm, it will give you probability that probably this query, which is wrong query, wrongly worded query, or wrong spelling query, is extremely related to this right one based on the based on the if the same elements are all, if the same characters are there in both the words, what is the order and what kind of algorithm you have implemented in physiology, right? So that I can think of, it will be sitting somewhere here before even going to the server. What else? We don't have local information. Each query will be different in for different type of local. If you in your own laptop, if you search in US, there will be a different set of queries. If you go to India, there will be different set of queries. When does that happen? So that local also is implemented somewhere here. This query weight generation, it will take into account the local for that query and local for you from where you are searching, and it will assign some weight to that. And whenever you query here, it will modulate that weight based on that and pick probably give you that result based on personal information, just like local. Different languages, what happens if your language is changed? If you want to search in Hindi, or if you want to search in any other language, Chinese, how do you do that? This all won't apply. Whatever you have done, probably infrastructure will still apply, but there will be so many different nuances based on the different type of languages. Then you have to create a different trie structure. It will have different algorithm, because creating trie structure for English is easy. As you can see, these are just characters. In Hindi, different aspects come together, right? Because the alphabet structure is different, the way they combine, that is different. You have to rethink your logic of creating trie structure and do that. Of course, underlying logic will remain same, but you can't just copy paste into another language. What happens if your query is capital sensitive, case sensitive, sorry, different cases, different queries? In that case, your basically database of queries will multiply multifolds, because till now you had let's say A to Z, only 26 characters to play with. Now you have A to Z plus capital A to Z. Now you have just double the characters to play with, and that will increase the set of character set in your trie data structure. If you combine with numbers and all other things, then it will keep on growing bigger and bigger. So you have to scale your structure based on that. Your simple partitioning scheme, which I just discussed here, right? You are going to partition based on the A to K and K to Z, won't work. You have to rethink that through. How about image searches? Again, different problem altogether. Predefined search boxes. If you I don't know whether I have rightly said it. I don't know what Google says it. When these days, whenever you Google some hot topic, then you don't even have to click a link. It already shows you on the top of your search list that probably this is the information you are looking for. You don't even have to navigate to that page, right? How do you collect that? You have to build something different for you have to build that component in your design, which instead of providing the list, all set of list, appends the relevant information which you have collected from that query, and you have to put that information on top of that list and then return to the client, right? And then I think the next thing which I am going to optimize if I am done with all these things is, don't just play on the number of words. You can play on the segment of queries. Till now we have been talking about that we were playing with the just words. I was suggesting the word, next word, next word, next word. Imagine these words replaced with some phrase, because Google doesn't suggest you word, it suggests you full phrases after you start typing, right? So you have to store phrases instead of just word. So that way you can return phrases. And yeah, one more last thing which I wanted to probably cover in this. What happens in Google search, or in general any other browser thing? Your browser also has a small cache. So if you have queried something today, then probably your browser, which is client, caches that query, caches its result on your page, probably caches that somehow the static page of that file, and saves it for some time. And after some time, if you do it that same query again tomorrow, then it will fetch even it will not even go to the server. It will directly fetch from your local database, local cache of that browser. So you can use that cache also. But as I told, this cache will be pretty small. It won't be of so much of use, but still it can be used to increase some consistency. And then, okay, one more last thing I wanted to say, which I was about to forget. In most recent clients, most up to date or good clients, what happens? The moment you type a letter, it doesn't fire a search query. There is a lag. The people who have developed the front end would know that when you develop a, such kind of text box which auto suggest things, you put a lag of some, let's say, 30 milliseconds. If I have typed some character, until unless I have a gap between next character and this character, the gap of 30 milliseconds, it won't fire a query. That client itself will stop from firing that query, because maybe it is expecting new letters before you form the whole word or something fully formed, then it fires the query. It reduces so much to and fro as compared to the firing of query on each letter. Understood why we are doing that? If you are writing tomorrow, then you start with T. One way is it will fire the query immediately. You write O, immediately one more query is fired. So every character will invoke one query. That is very not efficient, right? So if we are typing and there is not much gap between different letters, then it will wait for 30 seconds. And generally, it will keep on waiting. If you're not typing extremely slow, then it will generally let you finish whole word tomorrow, and then it will fire a query. Then instead of firing as many queries as the number of letters, it will fire just one query. So that's how we optimized on the client level. We at client level we added two things. One is local cache, and another thing is putting a lag in cache, lag in search. All right. Is there any questions left or explanations which you would expect from me?
Avnish, I think Deveshri is trying to say something on the chat.
Okay, let me see the chat. I can't see the chat, man.
On the Slack?
On the Slack.
Yeah. She was thrown out of the video or something.
Oops.
It's just me and you.
I don't know, it is asking me to. Hello.
Yeah, I see the join back.
Yeah, so I don't know what happened, guys. Somehow Slack uh, asked me to validate again. You guys let you admit, and this is weird. I think this is because between two sessions, first session and the second session, I updated my Zoom client, and probably that's something, a new feature of Zoom, which is like ask you to manually approve each one. That's how I missed. But anyway, I have recorded this session, guys. I'm done with almost all the talking, and I think you guys have to watch it on YouTube. But if you have any other doubt, then please go ahead and ask.
Avnish, I wanted to discuss the role of zookeeper.
Well, don't worry so much about the zookeeper actually. Think of zookeeper as of now some kind of reliable, very, very reliable configuration management software where you can put in entry and forget about it. And if hundreds of servers are asking for the same data from Zookeeper, Zookeeper is not going to go crash. There is, even after so much runtime race condition, still it is going to serve it. That's why we used a separate product. If this code, the same information is kept somewhere in such a resource like file, then if 100 clients are trying to access the same file at the same time, it won't sustain. It will crash probably. That's why we use Zookeeper. But I wouldn't worry about so much about Zookeeper. Even if you don't write Zookeeper, just write a simple store where you are storing this information, that should be enough. Okay, so let's think through what will be the questions from the interviewer sides. From interviewer sides, you will start with this, but you will not immediately go to try like I did. You will explain some kind of basic relational database structure, how you are going to store, and then you are going to demonstrate that why that particular thing is not going to scale well after a huge scale, and why do you need try in that case, right? You can, what I'm trying to say, you can store the same information of the search result in some kind of relational database. If you set up the tables right, you are definitely going to be able to store it. But will that be scalable? No, because these things are read heavy and you need good data structure to store that. So this is good structure. Try is a good state. And then you have to explain what try is, what try does, what it is meant to do, and why try is very fit for this condition, for this particular problem. And then you go ahead and design it. And while describing, just for the sake of discussion, for the sake of good discussion, try to have two different discussions for this one. First is how you are going to fetch the list of result, and another is how you are going to update it. So these are the things which I would keep in mind, just for the sake of discussion. If you combine all the design into one, definitely you can do it, but I think your discussion will become more complicated and you won't be able to convey all this huge information in one go. So that's why I told that probably you want to design in 2 steps. And then there will be follow-up questions based on these data. Once you're done with the design, then interviewer, if the time is left, then it will enhance the problem itself. It will say, what if you wanted to include so and so thing in my system design, how you are going to change it? Then you have to go back to your previous diagrams. You have to draw out new elements that probably that component, that software component, I'm going to put here, and that's how roughly it is going to work. I'm sure it will not go so much deeper, multiple levels after the follow-up questions, but you would definitely want to understand that how you are going to handle the change in requirement. All right. Any other queries? Okay, then I will assume no. Sorry guys, like I didn't see that because my this was on and my laptop was not showing me those notifications at that time. But after watching the video, even if you have any doubt, questions, you know what to do. Just message me on the Slack and I will reply. All right. See you guys next week with a new question, new problem.